So the valence bond description of multiple bonds is nicely illustrated by these three hydrocarbons. Two carbon hydrocarbons here, C2H6 ethane, C2H4 ethene or ethylene, and C2H2 acetylene or ethine. If we start with C2H6, here's the Lewis dot structure with the wedge bonds. We've seen that before. And what I want to point out is that each carbon has 4 electron groups around it, and therefore it will be sp3. And of course, each hydrogen just uses its 1s. So there are 2 kinds of bonds in this molecule. There are 6 carbon-hydrogen bonds. So in those, the carbon sp3 orbital overlaps the hydrogen 1s. So if we looked at that bond right there, that would be carbon sp3, hydrogen 1s. The other kind of bond is the carbon-carbon bond right there, and the carbon-carbon bond uses sp3 hybrids on both carbons, and so that would be carbon sp3, carbon sp3. So once you pick the hybrid, writing down the bond descriptions is pretty easy. Okay? Now each one of these bonds has end-to-end overlap. In other words, they line up in such a way that the hydrogen 1s lines up with the carbon sp3 to give maximum overlap, because the valence bond model says the more overlap you got, the more swagger you got. Okay? The tougher you are, the stronger the bond, so line up straight. Okay? And the reason for that is when you have end-to-end overlap between the 2 bonds, then the electron density focuses on that area, and it's therefore shared between the 2 nuclei, and Coulomb's law gives you the most for your money. So if we looked at a picture of C2H6, it would look like this. We would have the carbon-carbon bond overlapping 2 sp3 orbitals between the 2 carbons, and we would have the 6 carbon-hydrogen bonds being carbon sp3, hydrogen 1s. Now, when the end-to-end overlap occurs, forming a single bond, we call that a sigma bond, Greek sigma. Okay? And that's the reason there's a sigma right there and a sigma up here. A sigma bond is head-to-head or end-to-end overlap, straight-on overlap. That's what it means. And sigma bonds are always single bonds. Okay, so C2H6 is pretty straightforward. Questions on it? All right. I guess I said all that. Well, let's go to C2H4. Here is the Lewis dot structure for C2H4, which we've seen several times prior to this point. It has a carbon-carbon double bond, which we proved by writing its Lewis dot structure and getting octets for the 2 carbons. So as you look at the carbons here, each one of them has 3 electron groups around it, and because of that, each carbon is AX3, and because it's AX3, it uses sp2 hybrid orbitals. Okay, so as you look at this, sp2 hybrid orbitals are triangular planar, if you would, or trigonal planar. So this molecule, this section of the molecule is flat, and this section over here is flat, and that's because of the characteristics of sp2 hybrid orbitals. Now, to describe the bonds, we'll take the carbon, each one of the carbons, and we'll draw an energy level diagram like this, and we'll have mixed an S and 2 P's to get 3 sp2 hybrid orbitals, as we saw last time. Now, that will leave 1 p orbital, which is not hybridized, remains as a p atomic orbital, so we'll put it in its own little box here. Now, there are 4 electrons. 1 each will go into the 3 sp2 hybrid orbitals, and one will be left over for the p atomic orbital. We'll form the bonds by bringing a hydrogen in with its electron and forming a pair bond between the carbon sp2 and the hydrogen 1s. So each one of these 4 CH bonds will be a sigma bond by virtue of head or end-to-end overlap of the hydrogen 1s and the carbon sp2 forming a sigma bond. So there'll be 3 of those. 2 of them will be hydrogens. What will the last one be? It'll be a sigma bond to the other carbon using the sp3s, or sp2 and the other carbon. So we'll show this as carbon sigma, and it will be like the sigma bond in C2H6, except instead of using carbon sp3s, it'll use carbon sp2s. And I know that because there are only 3 electron groups around it here. Okay. So if I look at this molecule, and I remember that it's flat, I can write down the sigma bonds. There are 5 of them, and I've written them in here for you. 5 sigma bonds. This one is carbon sp2 to carbon sp2. So let me just write that in. Carbon sp2 to carbon sp2. And as you can see, that's a sigma bond. And each one of the CH bonds is carbon sp2 to hydrogen 1s. Okay? Now that leaves 2 p orbitals that are not hybridized, 1 on each carbon. And they are held in an orientation which is side by side, and each one of them has 1 electron left. This is 1 carbon here, the other one will look just like it. So the sigma bonds hold these 2 p orbitals together, and if they are lined up, they can overlap side to side like this. And when they do that, they form what's called a pi bond. And a pi bond is a bond that's formed by side-to-side overlap. And in this case, you could see there are 2 electrons that go into this pi bond. And so they will be here, but I'm going to write them down here too. Why? Well, even though this bond has 2 lobes, one above the plane and one below the plane, they are both involved in the pi bond itself. It's not like this is one bond and that's another bond. All of this is one bond, and because of the fact that it's due to side overlap, we don't call it a sigma bond, we call it a pi bond.
So that's where the carbon-carbon double bond comes from?
Yeah, the carbon-carbon double bond then comes from this sigma bond, is half of it, and this pi bond is the other half. So when you look at those 2 lines, you should think, oh, where did it go? You should think that one of them is pi and one of them is sigma. It doesn't matter which one you choose, but one of them will be the sigma bond and one of them will be the pi bond. Let me get back to where I was here. Okay, questions on the formation of the pi bond? Yes, go ahead.
Is that why the carbons don't rotate to keep the hydrogens further away from each other?
He is asking, why is this molecule flat? Maybe it could rotate like that. And the answer that he suggested is correct. If you think about this pi bond, the only way the pi bond can work is if the p orbitals are in the same plane. As soon as you start to rotate them, even a little bit, you have to break that bond. So the bond keeps the molecule flat. And I have a very short little story to tell you about an important molecule called rhodopsin that involves that subject in a few minutes. But yes, you're right. The pi bond keeps the 2 halves of the molecule from rotating. The 2 halves of the C2H6 molecule can rotate freely. They're not locked together. But this pi bond locks the 2 ends of the molecule together and makes the whole thing flat. Other questions?
Is like when okay, do the pair of electrons stay within like its orbital, or do like they all really go within all the orbitals?
The valence bond model says that the pairs of electrons are localized in their bonds. And for a pi bond like this, localized means it can be in the bottom part or the top part.
Well, because you said nitrous oxide is like it's more important for the oxygen to have a single electron, but in cool states, the nitrogen has a single electron on it, forms the bond between the nitrogen. So how do those electrons change their orbitals like that?
That's a different process. We're talking about combination of two molecules rather than the structure of one molecule. When you have two molecules, they can interact with one another according to the availability of the electrons and the availability of the orbitals. And the question is, in that kind of case, does that interaction produce a more stable di-molecule, or pair molecule, whatever you want to call it, or not? In the case of NO, nitric oxide, the molecule itself is quite stable, and you don't get much more by allowing those unpaired electrons to form a bond by overlapping between two of these things. The reason is complicated in the sense that you need molecular orbital theory to describe it properly. And on Friday we'll start molecular orbital theory, although I won't promise you we'll get to NO. We may not have time. Thank you for your question. I hope I answered it. Okay. Yes, go ahead.
What's the notation that you use to describe the C double bond?
This carbon double bond, you have two bonds. One of them is a sigma bond, and one of them is a pi bond. The sigma bond down here is carbon sp2, carbon sp2. The pi bond up here is carbon 2p, carbon 2p, and usually they'll go ahead and put a pi in front of it so you'll be sure to know exactly what you're talking about. And it's not unusual to have a sigma bond in front, a sigma in front of this description either. Okay, let's go a little bit further this and talk some more about pi bonds. The pi bond, all pi bonds, have lobes above and below the sigma bond axis and a node in between. Well, a node is something, all that we said about a node was it's a place where electrons can't be. And so you might wonder how the pair of electrons in the pi system gets back and forth. And remember, wave mechanics describes those electrons, and it doesn't have a problem getting through a node if it's a wave. So remember that the pi bond itself consists of two lobes, and it can hold a maximum of 2 electrons. One pi bond holds the 2 electrons, and they move through both regions. So electron density, if we had a density diagram, in the pi bond would be greatest above the carbon-carbon link and below the carbon-carbon link, because that's where these lobes of the pi bond are. You probably don't have a hard time understanding that if you compare side-to-side overlap with end-to-end overlap, that end-to-end is better, and side-to-side is not as good. And therefore, the pi bond tends to be weaker than the sigma bond part of this. It's not always easy to sort it out, but there is one piece of information that kind of tells you this. A carbon-carbon double bond has a bond energy of 614 kilojoules, plus or minus a bit. A single carbon-carbon bond is about 347 kilojoules. So a carbon-carbon double bond energy is not twice as much as a single bond energy. And the difference is the pi bond in the CC is not as strong as a sigma bond. And that's evidence for that. I will mention again this idea of the rotation. There is free rotation around a sigma bond, but the p atomic orbitals must be parallel. They must be lined up side to side in order to form the pi bond. So if you try to rotate them out of alignment from one another, you will have to break the bond. In order to break a bond, it's just like any other bond, you have to put in a bunch of energy. Now, energy can be put in various ways. But if you have this connection between the bonds, it will tend to hold the molecule in such a way that you could, if you look at the substituents here, you could have the isomers that we talked about before. In other words, if you were looking at dichloroethylene, it could be a Cl here and a Cl here, and that would be cis dichloro. And you would have a hydrogen here and a hydrogen here. Or the chlorine could be up where this hydrogen is, and the hydrogen could be down here. That would be the trans one that we talked about before. And those two can exist by themselves, even together, if you want. You can have a mixture of them. And they don't interchange unless you put in a lot of energy. Now, I want to just notice that if you look at cis dichloroethylene here and trans dichloroethylene here, both of them have a filled pi bond. In other words, a working sigma bond and a pi bond here. So both of them have a double bond, and therefore these cis and trans structures can exist when that's the case. Okay. In our eyes, as well as in the eyes of a number of different kinds of organisms, including mollusks, certain kinds of insects, various other vertebrates, there is a molecule called 11-cis retinal. And it is this long, complicated molecule here. The carbon chain coming out of this ring has a double bond between carbons 11 and 12, right there. So it's called 11-cis because the substituents around that double bond are on the same side. So they are, this would be the cis isomer, like cis dichloroethylene has the chlorines on both sides, on the same side, and this has the next carbon on the same side. Now, when this molecule is exposed to visible light, a very interesting thing happens. Nature somehow has tuned this molecule so that the energy to break the pi part of this bond is exactly in the range of visible photons. So along comes a photon and breaks the pi part of this bond, which is a weaker part, of course. And once that is broken, we have two free electrons, and we have a carbon-carbon single bond. So what happens? Well, the first thing that happens is this part of the molecule down here, this tail down here, rotates until the chain here is all trans. Now, when that happens, the connection between this big protein here and the retinal changes. When it's 11-cis, the whole molecule is held in close proximity to this big protein. As soon as the light breaks the pi bond and the thing switches around and becomes all trans, then it doesn't fit anymore. And this big end of it sticks out. And when it sticks out, it interferes with the flow of ions in that part of your eye. And when that happens, an electric charge develops along your optic nerve, as I understand it, and it creates an impulse. And your brain's sitting back there thinking about something else, and all of a sudden, coming in on the line is, whoa, I see light. I see something. It's a car coming this way. Get out of the road. It is a combination of photon energy being converted to physical energy, motion, and the influence of the new configuration of the retinal so that it's sticking out and interfering with ion flow. And that then is the key to the signal going down your optic nerve. This is a fascinating thing. The fellow who was one of the people who was responsible for discovering this used to work here at the University of Houston. And I remember him giving a seminar about this, and I thought, isn't nature amazing? And of course, after, as soon as this has happened, a process begins in which the 11 cis retinal is formed again, and it goes back to where it was, waiting on the next photon to come. Okay, so cis. Then we have this spinning thing here where the bond breaks, and now the backbone becomes all trans. And then this thing sticks out, and we get a charge, and the charge causes the optic nerve to flash. So there are a lot of things in nature that depend on the properties of double bonds. Questions on that? I hope you don't ask, because I don't know anything more than you already heard. I'm not a biochemist. So let's go ahead to another interesting molecule in nature. If you've ever been bitten by a fire ant, part of the potent concoction that the fire ant inserts into your skin is formic acid. And insect stings in general typically have some formic acid in them. It's the simplest carboxylic acid. So this question says, predict the molecular geometry of the molecule and propose a hybridization scheme for the central atoms that's consistent with that geometry. Okay, so the topology of the molecule has a carbon and an oxygen as central atoms, and it has, as you can maybe guess from this formula, it has another oxygen that's present there. This is an 18, that oxygen is connected to the carbon. This is an 18 electron molecule, and if you take the single bonds here, you put in the single bonds, there are 4 of them, so that's 8 electrons, so we have 10 electrons left. And those 10 electrons can be divided up like this. We can put 2 electrons around that, 2 pairs of electrons around that oxygen, and the other 3 pairs around this oxygen. That still leaves carbon with less than an octet, so we're going to put take a pair of electrons, a lone pair from the oxygen, and make the carbon oxygen bond a double bond. So what we have here, ultimately, is a carbon-oxygen double bond, 2 pairs of electrons there, and a carbon-oxygen single bond with 2 pairs of electrons on the oxygen as lone pairs. All right? So as we look at this, now carbon has an octet, has 4 bonds around it. That's a good thing. And we can now analyze this in terms of the hybridization. What hybridization will the carbon have? Somebody said it, sp2. Why? 3 electron groups. So the carbon has sp2 hybridization. And the extra p orbital that sticks out of the carbon will be instrumental in forming the pi part of the double bond that we put in there. And the sigma part of the bond will be carbon sp2. What? Oxygen. What will oxygen be? How many electron groups around the oxygen? How many? 3. 3 electron groups around the oxygen, so it will be oxygen sp2. So carbon sp2 for the sigma bond, oxygen sp2. And that's where the extra p orbital comes from. So that would suggest, if this carbon is sp2, that this whole part of the molecule is flat, because sp2 hybrid orbitals are flat. And if we look at this other oxygen, what hybridization would we expect for that? sp3, 1, 2, 3, 4. 4 electron groups, so sp3. And so what shape class would this oxygen have? AX2E2, like in water. So this thing will be bent. This part of the molecule will be bent, and this whole part of the molecule should be flat. And that's part of what causes the biochemical activity of this molecule. So here is the molecule. You can see the OH, COH is bent, and you can see the carbon on this end, the oxygen, the hydrogen, and the connection there is pretty well flat to make this work. Pretty flat. Questions about formic acid? Okay, is everybody comfortable with the process that we use? I know I build up the steps step by step, but if you miss one of those steps, you can be in deep water, so I don't want you to miss it. All right? If you feel pretty comfortable, what do you think? Put this double bond in there. What do you think this bond angle right there ought to be? The first ideal angle.
120.
Ideal is 120. That's correct. Then the actual angle, what do you think that would be?
Greater than 120.
Greater than 120. All right. You've been preparing, haven't you? That's good. Glad to hear it. So you can actually get down to fairly subtle aspects of the description of a molecule like this, just knowing what we know. Isn't that cool? It always makes the hair stand up on the back of my neck to think, gee, we can take these simple ideas and make pretty accurate predictions. And the Lewis dot structure for acetylene looks like this thing up in the upper right-hand corner of your slide. And we start off by asking the question, how many electron groups surround each carbon? I have volunteers in the front who know. What about somebody else who couldn't hear? How many? Can you count them? Well, if you can't, time's running out on you. There are 2, and therefore the carbon atom with 2 electron groups will assume sp hybrid orbitals. And it was right there anyhow, all along. So if you were watching, you could have seen that. So each carbon uses 2 sp hybrid orbitals, and it uses 1 for the sigma part of the carbon-carbon bond. I'm just going to say that bond in the middle is the carbon-carbon sigma bond, and it will be carbon sp, carbon sp. Head-on overlap, a single component to this triple bond. We have a triple bond. The Lewis dot structure tells us it has to be triple, otherwise we don't have an octet. Okay? Carbons don't like it when you don't have an octet. So the other sp hybrid is used to form the bond to the 1 hydrogen that exists on that particular carbon. So this is an sp hybrid lined up with a 1s hydrogen over there. Okay. Now, each carbon then forms a sigma bond to hydrogen. So this is sigma. And a sigma bond to the other carbon using sp hybrid orbitals. Now, if you look down here, there's one of the sigmas. There is the carbon-carbon sigma bond. And here is the other sigma carbon-hydrogen bond right there. But if you keep in mind just for a moment, the orbitals that we have to work with, if one of these carbons, let's say that one right there, used an S and one P to make two carbon SPs, to make these sigma bonds, then that leaves two P or atomic orbitals left over. In the case of C2H4, there was only one carbon P orbital left over. But now there are two. So we have to think about what might happen to them. You can see the picture of them here. There are two gray ones that are lined up here and here. And there are two sort of brick red ones lined up here and here. Okay. Now if you put the 4 electrons in, this is the key step. If you remember to put the 4 electrons in, there's going to be one in each one of these orbitals. And that tells us that each of these can form a bond to something else that overlaps with it and has also one electron on its own. So over here we have the other carbon, this carbon here. It has 2 SPs and 2 Ps. And to keep track of what's going on here, this carbon forms a bond to hydrogen. So this is a sigma bond to hydrogen right there. And it uses its other SP to form the sigma bond to the other carbon. Okay, so we have CH bond, sigma, and a carbon-carbon sigma bond. Now, that carbon-carbon sigma bond holds the p orbitals close together, side to side. And if they're lined up, and each one has an electron in it, which is what this diagram suggests, this one and this one are lined up together, they can form a pi bond. So we can get this. You can get a pi bond that looks like that. And the other p orbital is the same way. Lined up side to side like that, so we can get a pi bond from that one. So we take this one, line it up with that one, we get a second pi bond. So this molecule has 2 carbon-hydrogen sigma bonds of the ordinary plain vanilla variety. But then it has a triple bond, which is made up of a sigma bond, SP, SP, and 2 pi bonds. Okay? Here are pictures of the pi bonds once they have formed, and the gray lobes of this one and this one come from the 2 p orbitals that are gray over here. These two. And the ones that are brick red come from the 2 p orbitals that are brick red here. And you can see the sigma bonds in between. So this molecule has 3 sigma bonds and 2 pi bonds. And we can describe every one of those bonds by what atomic orbital or hybrid orbitals were used to form it. Okay? This is, whoops. Come on, back up. You can do it. Okay. 2 lobes of each pi bond make up the bond. Sometimes there are questions that appear in your homework. It says, how many lobes are there in this pi bond? And sometimes it says 1, sometimes it says 2, sometimes it says 4, all kinds of things. You know there are 2 lobes in each pi bond. Okay, to finish up today, I want to go back to our old friend, the acetone molecule. And we did the Lewis dot structure of the acetone molecule. And we came back to it later, and we predicted its shape, and we showed that the carbons and the oxygen are all in a plane. And now we can look at the bonding in terms of the valence bond model. And it works very well. We look at the 2 CH3s, just like the CH3s we've seen before. these carbons are AX4, and therefore they use sp3 hybrid orbitals. So this carbon and this carbon use sp3 hybrid orbitals. The carbon in the middle, this one here, has how many electron groups around it? 3 electron groups around it. So that carbon needs to be not sp3, but sp2. And it can use its 3 sp2 hybrid orbitals to form these 3 bonds. This sigma bond between the center carbon and this CH3, and this one between the center carbon and this CH3. And then the carbon-oxygen bond it's a double bond, so it has a sigma, and the sigma will be carbon sp2 to oxygen what? What's oxygen going to be? How many electron groups? 3 electron groups, so oxygen is going to be sp2. So this sigma bond right there will be sigma carbon sp2, oxygen sp2. And the pi bond on the other side is carbon what? Carbon 2p, it's the leftover p orbital, and oxygen 2p. Or carbon p and oxygen p, if you will. Okay, so here is the picture of all the sigma bonds. These are the sigma bonds that we have in here. And notice that oxygen sp2, carbon sp2 has head-on overlap. So that's a sigma bond. Notice also that the lone pairs on the oxygen are in sp2 hybrid orbitals. Question? No? They're in sp2 hybrid orbitals. So that means if you could see the electron density around the oxygen, this part of it would be in a plane and flat. But you've got to remember that there's also a p orbital sticking up out of this and sticking down, and one that's sticking out of this and sticking down. And that is the basis, the side-by-side overlap with that p orbital is a basis for a pi bond. I think you can see the rest of this. You can describe all these bonds. We've done that before. So if you just focus on the pi part of the carbon-oxygen bond, it'll have 2 lobes. There's a pair of electrons somewhere in there, and those 2 lone pairs on the oxygen, and that gives us everything we need to know about that molecule. If I ask you what is the description of that bond right there, you ought to say it's a sigma carbon sp2 to oxygen sp2. And if I point to this carbon-carbon bond here, write down on your paper what that one is. See if you can write it down. If you can't write it down, you haven't been paying attention. Write it down right there. Is it a sigma bond or a pi bond? It's a sigma bond. And it has 2 carbons, so I'm going to write the first carbon as this center one. Sigma carbon, and then what am I going to say? sp2. Then I'm going down to this carbon, and what will that carbon be? sp3. Does everybody see the method, the madness, you might think? Okay.